Yeah. Well, good morning, good afternoon, good evening. I'm on the West Coast, so it's morning for me. Thanks, Chris, for the previous talk. The what I want to talk about today is how, and as you said, how we're versioning our Terraform at Kong Cloud. But in particular, at the end, we're going to spring into what we're doing with that with Nomad as well, and so it's always interesting to hear other use cases about Nomad. So this was a good jumping point to be able to dive into that. So yeah, we'll get into it. We're going to talk today about again what my team is doing with how we manage our Terraform dependencies, how we're versioning things, how we're deploying them. Really, sort of more of a culture and design choices around how we're building our Terraform, and then a little smattering of tooling that's going to go into that as well. So brief introduction. My name is Robert Paprocki. I go by Poprocks. I'm a cloud engineer at Kong. We build an open source API gateway. We also have a cloud SaaS product that we work on. That's the team that I build out and work on. Previously, I was an engineer at ZenEdge, DreamHost, Blizzard, various organizations doing AppSec, InfoSec, and systems engineering. I've contributed to a handful of HashiCorp projects, Terraform, the vault provider for Terraform. I gave a talk at HashiCorp last year about our work there, as well as the Nginx and OpenResty projects. And I am known to get into, as a colleague of mine put it, shenanigans, hooliganery, and no good nickery from time to time. So as I was sitting down to work on this talk, I kind of had to sit back and think a little bit about what a Terraform module actually is. And thankfully, the folks at HashiCorp have done such a wonderful job with the documentation. The first sentence in the docs for Terraform modules answered it for me. A module is a container for multiple resources that are used together. And one of the things that kind of struck me about this definition is that it feels a little intentionally nebulous. There's not a very strict API or design or really any set of paradigms around what a module is or isn't. It's just a collection of resources. And that allows for teams to develop their modules and their Terraform in ways that work best for their teams. You can write modules that are very large and all-encompassing and handle specific roles within your organization or what you're deploying, or you can write modules that are very small, very pointed, have very thin interfaces that really only spin up one or two resources. There's a very large range for flexibility there. So defining a module, or rather calling a module, is simply a matter of using the module keyword in Terraform and pointing it to a source. And that source can be somewhere local on your file system, a Git repo, something inside of Terraform registry, and then passing it to parameters, which are just defined as variables inside of that Terraform code. Folks that are familiar with Terraform, this is pretty one-on-one stuff, but this is a good overview. And being able to visualize this is really important to being able to step forward and understanding how you might use a module. So clearly there's a pointer to where the code lives, and there's an interface for defining parameters that are going to be used, but the actual implementation is abstracted away by the module itself. There's a couple of different use cases as we sat down and sort of pinned out how we were going to rework some of our Terraform as we've embarked on digging more and more into HashiCorp tools and figuring out why we actually want to use modules and why we wouldn't just have a monolithic repo that just holds all of our single Terraform code, and then we would just run a single Terraform apply. And these are all listed out here. And what I really want to pin on, in addition to versioning, which we'll get to in a second, is the notion of abstracting away a lot of the implementation and being able to reuse that. And even though the implementation itself is just Terraform resources, as your Terraform code gets more and more complex, it's really, really important to have an interface that simplifies that. Because as an engineer, I don't necessarily want to spend a whole lot of time writing out a bunch of plumbing code or rewriting a bunch of plumbing code when there's an existing pattern that I want to use. If I have Terraform code that creates a worker pool of EC2 instances and backs them with EBS storage and sets up an accompanying RDS and a load balancer, I don't want to go through the rigmarole of copy pasting that into new code, making sure I didn't, make any mistakes, making minor modifications and having to manage a whole bunch of duplicated boilerplate. So it's really important for me as an engineer when I'm creating out new infrastructure that I can reuse any existing prior art that I have. I took a look at one of our modules, and this is just a small subset of some of the resources that we're using. And I cannot imagine having to, every time I wanted to create a new environment, even a testing playground, having to go through and figuring out everything that's going on, reduplicating all of this. If I have an environment where I just want to say, hey, you know, that thing that I created last week, Tuesday, I want to do that in another region, great. Give me an interface to do that. Don't make me recreate all of these resources over and over again. And that's what modules in Terraform let us do. So as an example, for what we do, I mentioned the notion of worker pools, which would be Nomad clients is an example for us. A lot of that logic is the same. They have particular SSH keys that they're given. There are particular ways that we deploy auto scaling groups and spot requests and things like that. And only a few things are going to change. And so in this case, I would want to define one pool with a certain number of servers with a smaller set of local volumes of type M5 large, just M5 large instances. And then I might want a separate worker pool with a slightly different tweak. I need a little bit more compute power. I need a little bit more disk, less of those resources. Again, I don't want to have to go through, duplicate all of the Terraform resources. Abstracting that away in a module lets me write 5 lines of code, not 500. So we'll get into versioning. And as we sort of, again, as we sat down and embarked on this journey, I kind of had a hard time understanding why versioning was important. A lot of my past engineering experience has been very much pointed to, merge on green, deploy on green. If it's in master, that's the state of the world. And so I can just look at the master branch of my Git repo and know that this is what my infrastructure looks like. And so I had a hard time sort of grasping why we would necessarily want to do this. And we could really borrow a lot of the same concepts from software engineering. If we're testing a new feature, or there's a notion of bleeding edge versus stable in a module that you're providing for your team or perhaps other engineering teams in your organization, it's important to be able to have a known good set of code and to be able to potentially branch off of that. If you're using semantic versioning in your modules, having a notion of breaking changes versus new features versus bug fixes only, because your module provides an interface and abstraction, the notion of being able to semantically define what your module does and doesn't do with respect to different versions becomes really, really important. If you're providing an abstraction layer and other folks are using that abstraction layer, it becomes critical that only your, the interface that you provide is other folks can expect to know what to do with that, and documentation works well. But if you're building a module that's evolving constantly and changing, that interface breaks for somebody who's not keeping up with the hour by hour, day by day, or week by week changes inside of your module. And so being able to provide for semantic versioning, being able to communicate out to your user what your module is doing and how things are changing at different rates becomes very, very important. And this is also important for managing different providers as well. There's substantial changes between different versions of Terraforms. There's substantial changes between different versions of complex providers like the AWS provider. And so having sort of a legacy version or set of releases for one module that would be designed for version 1 of the AWS provider versus version 2 or version 3, being able to draw a line in the sand there becomes really, really important as well. So versioning within modules on the face of it is really straightforward. You just define a param called version, and this is going to work out really, really well, except when it doesn't. There's a bit of a problem with using this notion of versioning in that it's only supported for modules that are hosted on the Terraform registry. And there are more, Terraform registry is not the only place where your modules may live. They might live in a Git repo on GitHub. They might live in a Mercurial repo. They might live somewhere else entirely that you're just accessing through somewhere on your local file system. And so it's important to that we can version modules, not just through a way that's only supported by one way to host modules, but as many ways as possible. So with Git in particular, which is how we're deploying our Terraform, there's this notion of pulling a repository from GitHub and then using this ref param. And this can point to anything that can be checked out by Git. So this might be a branch name, which it is in this case. It might be a version tag. If you're doing version pinning, a particular checkout ref or a commit ID. Anything that can be checked out, it can be used here. This sort of leads to this anti-pattern, at least that I found, where all of your sources have this var version variable, which besides not being too aesthetically pleasing, in my opinion, it ends up being really, really hard to manage because you're now constantly pointing different versions through variables into different repos and managing more and more variables inside of your Terraform code, which can start to get really unwieldy. And so this is what this would actually look like is just doing this variable interpolation here. And if you imagine if you're loading tens or hundreds of modules, have tens or hundreds of different variables that you have to maintain, trying to keep track of what versions go where might start to get a little bit unwieldy. Oh, sorry. So there's got to be a better way. And when asking questions like this, for us, it was really important to understand that the question wasn't, is there a better way? It's, we know there's a better way. And so we set out to find that. So this is where we started to use a tool called Terrafile. And there's a number of different shoot-offs. There's one that we started looking at very recently called Xterrafile as well. But Terrafile is a very lightweight binary that's used to sort of ease version management in modules. This is not something that we've developed. This is an outside project, but we started to take advantage of it. It's very, very simple and it's very lightweight. Under the hood, there's really only two things that are going on. There's a very thin type definition inside of this Go binary that defines what your module is. So essentially you point it to some source code and you give it a particular version. And this would typically be semantic versioning, or again, anything that can be checked out. And under the hood, what happens is a single exec call to get that clones this repo that you're given based on the version and where this is located. And so this is a very, very thin utility, but it simplifies a lot of the plumbing and extra Terraform variables that I mentioned earlier. So one example from one of our deployments that we have looks like this. There's a single module that we check out, and this actually is a mono repo that we're using, and we're pointing it at a particular version tag, which in this case is just a git tag that is 023 in this case. A quick note about monorepos is a slight tangent. I don't know that I have very strong feelings one way or another. For our use case in particular, what we found is that it helps keep everybody on the same page because you don't have a number of different Git repos flying around. And it also simplifies the deployment here. There's only a single repository that we need to check out. And as different tags evolve in that repository, it forces your team to continue to make small changes inside of the repository itself, which means small changes in your modules, which keeps a faster feedback and a faster development cycle, sort of a central focus among the engineering team. So things don't spin out of control and you don't have feature branches that are living in the wild for days or weeks or months. It forces everybody to stay on the same page. So I know that's kind of there's plenty of discussion to go back and forth. I think what we found is that a monorepo for modules, because those modules are called elsewhere, makes a whole lot of sense because the module code itself essentially just functions as a library. And so there's a handful of ways that we're sort of segmenting out the code in our deployments. We have a notion of a few different entities when we deploy Terraform. First is the VPC. So where are we actually deploying? In this case, we have a VPC called Kong, where we're deploying Kong. And inside of the file structure, that's denoted by the parent directory here. Next would be the module itself. So in this case, a worker module, which for us is an autoscaling group, the nodes that will join a Nomad cluster, a load balancer, potentially RDS, or other accompanying AWS resources that we would use instead of a Nomad managed workload. We then have a notion of what environment we're in, dev, QA, stage, prod. And this lets us, follow a similar life cycle with what you would find in other organizations where, you're going through and you're very aggressively writing code into a dev environment and using that as a playground to test, and your production code generally sort of lags back in this development a bit. And then finally is the region, as we're deploying in multiple regions, as we're expanding operations, being able to segment this out and deploy specific versions of code, as a canary in one region, or just if there are limitations on the region that you're in. For example, US West 1 only has 2 availability zones if you're on AWS. So being able to segment this out by region is also very important to us. Actually deploying this code is relatively straightforward. So we have the 4 elements that we had, what particular module that we're deploying, what kind of VPC it is, where we're deploying it, and what environment this is. And this is all handled through some bash tooling that, again, uses Terraform under the hood. We don't necessarily need to go into it. But again, what this gives us is a very simple interface for us to be able to deploy. And a lot of the plumbing under the hood is taken care of for us. So we have a lot of different modules. We have a lot of different code, a lot of different resources, and those are going to be interacting with each other. And dependency management here started to get a little bit tricky. When we first started writing Terraform code, we had a lot of this pattern where we would call a module in one case that defined resources. So for example, on the left, we have a module that creates a load balancer and makes available the DNS name for that. And then a separate caller or a parent module would load that up. And then if we needed to feed the output from the first module into the second, we could just reference the module directly in Terraform. And this works really well because Terraform automatically manages all of the life cycles for us. When it creates its dependency graph, it knows that it needs to create the first module before the second. And this is where the power of Terraform really comes in, is all of this logic is handled away for us. And it works well until it works well when your dependency chain is very linear and you don't have circular dependencies, or you don't have modules that necessarily depend on each other. When you do, you start to run into some limitations of Terraform where when the plan phase is run, some data may or may not be there before the actual application phase of Terraform runs. And so we started to adopt a pattern of using softer dependencies. When data for a particular resource was needed, instead of being exported through Terraform directly and having that written into the Terraform state and having all of our modules in one repo and in one deployment, the data was just read in from the module that needed it through a data resource inside of Terraform. We would use the data provider to load, for example, in this case, the load balancer name, and be able to access the DNS name indirectly, as it were. And so this works out well because there are now smaller state files. You have more individual repositories and individual modules that are called, rather than a single large monorepo of calling code. I had mentioned that our modules are in a monorepo. The actual callers of the modules where we're deploying are individual Terraform states. So this means that deployments are faster because the Terraform state is smaller, and so the sink is smaller. And it also means that we now have sort of a provider-based definition of our infrastructure, where there are specific cases where we're only looking at deploying Amazon or deploying Nomad jobs through Terraform. And again, that interface is very small for our calling Terraform code. The problem with this is, as I mentioned, the notion of circular dependencies that Terraform couldn't resolve in the previous way to do dependency management, that's still here. If you have a load balancer that references a security group and a security group that references a load balancer, you still have the chicken and egg problem. Terraform won't necessarily be able to resolve it on your own, but when you have sort of soft dependencies here, you have to do that management on your own. And that was some of the biggest challenges that we had as we grew sort of out of a greenfield way of doing this to actually running with multiple providers, running in multiple regions, running more complex deployments. So with this notion of inherent dependencies, where you're using data blocks to load up data, it's important that your modules get run sequentially. For example, if we have a module that depends on the VPC subnet IDs, the VPC obviously needs to be deployed first. So we can't just in parallel run all of our individual modules, deploy them all at once, and hope that things magically resolve. They need to be written in the right way. And so we needed a way to sanely define our dependencies, and we wanted to do that using the same tooling that we built out for deployment. Terrafile doesn't have this out of the box, but because it's YAML, we can start to extend this. So in our definitions, we've added in this notion of a dependency of a module. So in this case, this is taken from a worker module. So this, again, would deploy an auto-scaling group for Nomad clients. This module requires that the VPC is in place, and what we call controllers, which would run the console server cluster, the Nomad server cluster, and the Vault server cluster, as well as other controlling resources like a GlusterFS volume and things of that nature. These must be in place, and they must be deployed before this module can be deployed, before this worker can be deployed. Again, this isn't something that is defined in Terraform, but because the definition of what the module is, where it is, and what version lives inside of this YAML file. Extending it out to here was the natural approach. So we sat down and we asked ourselves what our dependency management requirements were. Each module will have 0 or more dependents, and it will have 0 or more dependencies. Once dependencies have been resolved, the module should be applied. And we started thinking through and we thought this sounds a little bit familiar. And then we realized, yeah, this is exactly what Terraform does. And under the hood, what it is a DAG. And there's plenty of prior art that's out there. And we definitely didn't need to reinvent the wheel. So we started looking through different tools and scripts and libraries that implemented a DAG to start to build a thin little bit of tooling around this. And we stumbled upon a small utility called tsort. And one of the things I love is studying a problem, trying to come up with a solution where there already are solutions, but thinking I'm going to need to write my own tooling, and then finding a GNU command line utility. I think this is a blast. So tsort handles this for us. We feed in all of the module dependencies. We pipe it in through standard into this utility, and it gives us the correct ordering based on the dependencies that we define. So no need to go through some Go SDK or write a Perl or Python script to do this. Just a single GNU utility handles this logic for us. So again, taking the notion, a couple examples, we have a worker that depends on a VPC to be in place, a controller cluster to be in place, and then we have a Terraform job or a Terraform module that would define a Nomad job for, say, Grafana, and Grafana would depend on the worker to be in place, as well as another module that makes Prometheus available to be able to visualize that data. And so we have this notion of dependencies, having other dependencies, and as long as we aren't defining circular dependencies, tsort can resolve things. And the end result is, again, a small script that we feed in. This is a small example of our modules. This is not the exhaustive list by far. But we get out from a top-down order of, at the top of the list, the first thing we want to deploy is our VPC. Make sure that's up to date. If there's any resources that need to be created, create them. And this gives us the advantage of whether we're deploying existing infrastructure or deploying new infrastructure in an entirely new region. Deploying these things in order is going to have the desired effect. So we first deploy the VPC, then our controllers, then a local worker pool, and then logical jobs on top of that to configure Vault, to set up a Prometheus server, all of our logical software definitions as well. So previously, again, I showed off this thin script that we have that actually does this deployment. Taking into account the dependencies that we've built becomes very simple as well. Again, it's just a matter of iterating over our thin tool that uses tsort to build our dependency graph and put things in the correct order. We just have to loop over that and use our existing tooling. And so we were able to use our existing tooling without having to build new libraries, without having to build new command line tools, without having to really shake up our pipeline, and manage our dependencies without having to do a lot of cross-module data references inside of Terraform, where we're loading remote state modules or things like that, which we've seen complications with in the past. So as we broke away from writing very large singular sets of Terraform where the entire VPC and all of the resources were in one module to small modules, this did require a bit of a shift in our culture thinking. Writing small modules became very tricky. It was very easy for us to say, well, here's a worker pool. It has an auto scaling group and it has a load balancer. It needs a KMS key because we want to do Vault auto unsealing. Let's just put the KMS key in this module. It was very tempting to continue on with that pattern, forcing ourselves to write small self-contained modules that really only did one thing, and using indirect data references was a bit of a challenge for us. But we think that ultimately it's led to a lot more cleaner code, code that doesn't necessarily have messy dependencies, and code that's a lot faster to deploy. So we've got all these Terraform modules. This is great. We've got a really well self-contained way to write our Terraform. And this is great when we're managing infrastructure, when we're managing things inside of AWS. And then we sort of thought to ourselves, what if we could do our software deployments in the same way? Previously, we were using Puppet for a lot of our logical config management. and that worked out well, but it was an extra tool in our stack that we didn't necessarily want to be running. So we started looking at Nomad for scheduling, and I really, really love the integrations that Nomad has with other tools. HashiCorp has done a fantastic job of Nomad integrating with Vault, integrating with Console. The entire ecosystem plays very well together. And in particular, it plays very well with Terraform. Because now, since there is an official Terraform provider for Nomad, the same tooling that we have, the same pipeline that deploys our auto-scaling groups, that deploys our VPC, our security groups, can be used to deploy our logical job definitions. We don't have to have multiple tools. The same pipeline, the same dependency management that runs our underlying infrastructure runs the logical software as well. And that simplifies things for us greatly. We did get to a point where we were abstracting things a little bit too far away. My initial thought was, well, we can just write if we want other teams to be able to deploy on our Nomad cluster, they don't have to learn Nomad HCL. They can just write Terraform and they just tell us what image they want to run and how many resources. And then things, the feature creep started to add up. Well, you need to be able to configure templates. You need to be able to configure ports. What if they don't necessarily want to run Docker? And so trying to abstract out the entire Nomad job into a Terraform module got to be too much. So we needed to come back to it again. What we settled on is the notion of just defining a very small module that will talk to Nomad, but the caller passes in the template file. So it's totally up to the caller to define the Nomad job. But this makes the interface very, very small. We have this notion of whether or not a job is public. And one of the things that the Nomad module will do is just automatically create a Route 53 record just to point it at our worker pool. And again, I want to highlight how we're doing this dependency management. So when we're creating this record, we're not passing in a Route 53 zone as a variable. So the caller doesn't necessarily need to know what the Route 53 zone ID is. They just need to know the name of the zone. We can load this up from data and be able to apply this directly without burdening the caller with having to know that, managing that in their own state of their own variables. So again, to wrap up, we're taking the module dependency, the module versioning that we've done for our infrastructure, for our low-level resources, for IAM principles, VPC, and we're able to reuse that to deploy our logical software as well. This gives us all of the power of Nomad with respect to integrating with other tools, versioning, canaries and blue-greens, rescheduling, all of that automation. The fact that we no longer have to write our own tooling for that is very, very advantageous for us. That's a bit of a wrap. I think I've got a couple minutes left over. So if we have any questions, we'll stop the share. And thanks everyone for letting me talk at you.
Awesome. Thanks, Robert. Let's see, it looks like we've got one question on the Zoom Q&A here, and that's, did you explore TerraGrunt and how did that work out?
There was when I was working at Blizzard, I recall there was a team that was using TerraGrunt pretty extensively. My team didn't look at it, and it's not something that we've explored here. I don't necessarily know that we've had a need for it. My understanding was TerraGrunt was written a couple of years ago to start to overcome some of the limitations earlier on in the Terraform language and some of the limitations that were there. And if I'm way off base, please correct me. With the opportunity to rewrite a lot of modules and being able to start fresh, as it were, we're able to leverage Terraform 0.12. And so being able to use more of the dynamic constructs and more of the functionality there has made things easier. So we haven't really needed to augment the actual Terraform itself with an outside tool. Really, it's just been versioning management with Terrafile.
Sounds good. And it looks like we're seeing one in the YouTube chat here, and that's, did you think about using Airflow to manage building your Terraform modules to handle failures, etc.? Also, there is a Nomad operator in Airflow that we have leveraged.
So we're doing some internal tooling now that has its own additional dependency management, and we've started looking at Airflow. I also recall reading a GitHub issue, and I think it's a little bit long in the tooth, about Nomad job dependencies. And this is not really Terraform specific, but related to Nomad. I know there's been some discussion about integrating Nomad with Airflow to handle more of that complexity. I don't think any of that work has been released yet. I think a lot of that might still be sort of under the hood investigation on HashiCorp side. So we'll be keeping an eye on that. I don't think we'll need it for Terraform, but for our more complex Nomad jobs where this Terraform dependency doesn't quite work out, we'll be looking at that in the future.